Hello, welcome to Engineers Ireland. Today we're going to look at integration, and after this particular one we'll be heading on into the special question, where you will find a little more integration, a little more differentiation, a little more series and sequences. So this is a heads up for you that, having looked at this one, revise your series and sequences and your differentiation. Okay, to integration. What is it? Well, there are a lot of, there are an amazing number of problems in engineering, science, etc. that you cannot really solve without integration. So the first thing it is extremely important, so it's something well worth learning. The second thing is it's often referred to as the inverse or the return journey of differentiation, and there's a lot of merit in that. It's also it also has its own interpretation, and you will see that interpretation when we get towards the end of this talk, when we're looking at finding the areas under particular curves between that and the x-axis, or rotating a particular curve to get a volume. So to begin with, let's take it from the reverse journey from differentiation. You'll be well fed up at this stage of seeing me draw this little drawing. Equation of a straight line. We know the slope of this straight line is m. So, and the intercept is where it meets the y-axis. This function, we can call it y. If we differentiate this, obviously, you'll get it's mx. Sorry, you'll get it as m. I had a long day yesterday. I'll write it out properly for you. You find, having differentiated, you get an answer m, and we know that when you differentiate something, what you're actually getting is a slope, and we've shown it in this simple case that the answer from the differentiation is actually the slope of this straight line. So if we reverse this game, if we integrate, and we'll now go the integral of m dx. That's how it looks, but how do we get to that? We get to it by starting back on this line. Let's say dy dx equals m. If I multiply across by dx, that means dy equals m dx. What's dy? Generally d is the first letter for delta, which just means a small bit. So we're saying a small bit of the y is equal to m times a small bit of the x. If we want to know what all of the y is, we will bring in an integral. That funny shape is just an elongated, strange looking s, which is the first letter of sum, where we sum up all the dx's, and it's also the first letter of sigma, which is really the nice mathsy way of talking about sums. So we're saying the integral of dy, which is y, and we will get m, and when I add up all the little bits of x, I expect to get x. Now the real issue is this is not that. What we have found is this line. That's y equals mx. So for an infinite number of lines, because it's an infinite number of different c's, if we differentiate it, we will find the slope of all of these lines with the same slope, which would be m. But if we integrate, we actually find mx, which is, I suppose you will call, it's the base camp one. It's the one that will go through the 0, 0. To show up the fact that we haven't really gone the full reverse journey from differentiation, we do add in a constant. this constant of integration here is probably the most thing that they're looking for in the part A's of the Leaving Cert integration questions. You will generally find that the part A's all have integrals that don't use limits, which we'll talk about in a minute. And even though you may integrate it, if you don't put in the plus C business, you're losing marks and you're wasting them without any real excuse for it. So be very careful in your part A's to make sure that you're putting in your plus C. Right, let's look at it then, and we're now saying we will reverse what we're doing in differentiation. We would say that this is f of x, and in differentiation we have x to the n, and if I get the dx of each of the things down here that we will write down, I'll find n x to the n minus 1 we would expect that if we were to go and integrate this, that you'll get this guy. Integrate this, we should get this. Minus sign should give you cos. So if we now look at the list that you will find in your logbooks for integration, you will notice that x to the n, and this will be for these functions. What's this telling us? Differentiation tells us x to the n. If I want to find the slope of that function, it's n multiplied by x to 1 less power. If we're to reverse it, we're saying if I had x to the power of n, I will expect 1 bigger power, and clearly I expect this down here because, and we will just look at it now, if I have my n plus 1 x to the n, I'd expect that that will give me x to the n plus 1. This thing here is mirroring this guy here. So that's the first of them. If we had a 1 over x, we will expect log x. It's on account of this. Cos x goes to sin x. Sin x goes to minus cos x. Now tan will give us a different one because over here we haven't seen tan come up as an answer. Okay. Differentiate cos, you get minus sine. If I was to multiply across both of those by minus 1, I'd be saying differentiate minus cos will give you sine. So therefore, if I integrated sine, I expect to get minus cos. The sine cos one is easy. Differentiate sine, you get a slope of cos. That means if we integrate cos, we will find an answer of sine. The reason I'm starting here is later on when we're looking at rules for dealing with quotients, where a function is divided by a function. You're generally supposed to use either all or part of the lower part as the u for a substitution. And it says be guided by what's on top. And this really is, I think, what is meant. because we're using the lower one as a substitution, we will hopefully find that the top part of it is the differential of it. Okay, we would, if we're using log as a u, we'd be looking for something like that on the top end of it. So for integration, you need to often refer back to differentiation. Those are just a few idle comments thrown in at the moment, so as you see that there's reasons for looking at both together when we're dealing with integration. Integration doesn't have the benefit of very handy rules, let's say like the chain rule which we have in differentiation. So very often you have to look at something and find what it's like, which would be a simpler thing, and work in that basis. Now let's start with pretty obvious stuff. The integral of some constant by a particular function, which we can call u, and I'll write it differently down here for you. Well, actually I'll do it over here. The integral of c. The reason we're using u here is to get you guys used to the fact that we will be using lots of substitutions in here. And we're saying, what happens if I've got some function which is called u multiplied by a constant? And we'll say a constant can be pulled out. That's a first rule. Here's a second obvious one. If I have two functions, u plus or minus a v function, and that is the same as the integral of we'll pick an example to show both of these together. And we'll do it the long way. Sorry. And if we go to the first rule of it, we are now wanting to find the differential of x squared. That's x to the n, and we know the answer is going to be 1 all over n plus 1 multiplied by x to the power of n plus 1, and we have 2 times it here, so it's going to be 2 over 3 x cubed, which is 2 by 1/3 x cubed. I'll write it the long way again. It's 2 outside of 1 over 3 x cubed plus 3 by x. It's important to remember that the integral of dx is, let's add up all the little dx things, and if you add up all the little delta x's, they will total x. So the integral of dx is x. Don't forget you have to add in a constant. We will pick another easy example because there's a lesson to be learned in this one. and you will find that this is one of a particular type which we will discuss later on. You will notice when you look at the log tables and you look at the area in relation to integration that there is lots of highly stylized type of, if it looks like this, the answer is like this. A lot of integration, or how you use it for the leave insert, is very much follow recipes. There'll be a standard recipe and you're supposed to see what I have, is it like something? And if it is, can I make a substitution to transform it, and then I can use the recipe. So in this case, what are we going to do? We're going to play with one of the standard ones. We want to integrate that. It's the square root of some number minus some number squared minus a function squared. And the answer is sine, the angle whose sine is x over a plus c plus a constant. Now we can see that this is clearly and now we have it in the form that we want. It now looks like that underneath the square root sign. So it's inverse sine x over 3 plus a constant. There are quite a number of those that are defined in your logbooks. We have, as well as this one over here, we have, I'll spend a little bit more time writing that here. What if it's that one? Notice we've looked up here at a squared minus x squared. Down here it's the plus. What difference does it make? That gives us the log of the absolute value of x plus kind of a complicated answer. The good news is you don't have to know where that came from. You just have to be able to recognize that what you have been given can be brought into a form like this, and then you immediately just use this. It's very much let's follow recipes. Okay, what other recipes do we have? We have x squared plus a squared, and this time there's no square root. That gives us an integrated answer of inverse tan x over a. And there are several more. So the first thing you realize is we have to turn something into a standard, and then we just pick the recipe answer. We'll pick this example. What does that look like? Well, there is a square root underneath the line, and there is a minus x squared, but unfortunately we got this guy here. what we want to try and do, we're seeing that it's very similar to this thing. And if we know that, we'll know its answer. What we want to do is the same thing that we've done in algebra, particularly in algebra, and it also turns up in geometry, where we would have a quadratic or a cubic equation or some set of relationships which have inequalities involved in them, and you try and set up squares, and in this case we'll do the exact same thing. Let's look at this. This is the same as the integral of dx all over, and we're saying I've definitely got a minus x squared, so I want it in this form. So we're saying the square root of 5, and there's going to be minus a certain amount of stuff now, and we'll say that means I have a minus 4x plus x squared inside my bracket here, and I'll run across the screen just to save myself space. And now I'm looking to form a square in here. Just to remind you, we know that the number multiplying into the x is going to be twice what we require. Going to be minus 2, and minus 2 squared is going to give me, now what you notice is if I remove the bracket there, I've now got a minus 4 in here, which means the total free number now is 5 minus 4, which is just 1, and I had started with 5. So because I've this minus 4 here underneath my bracket, I'm going to add 4. And that 4 is outside the bracket. So I have the dx of 5 and 4 is 9 minus we know 9 is 3 squared. So I now have this in a form that's very useful because it's a lot like this. We have to deal with this guy though down here, and you deal with a lot of these things in integration by using a substitution, and we can say let u equal x minus 2. Now that's nice and handy because we will have a minus u squared underneath. However, we don't know exactly how to deal with this yet, because I haven't told you. We want to be able to substitute dx by a du and other bits. So this is again where you find that there's a throwback to differentiation. You differentiate it, du dx. It's 1, and if I multiply across by dx, du is equal to dx. So I can substitute it. So our equation here can now become the integral of du all over the square root of 3 squared minus u squared. And we know from up here that that is the angle whose sine is u over 3 plus a constant. We also know what u is. It's worth your while getting experience in forming the squares. The only important thing to recognize here is once we knew it was a minus x squared, it was definitely going to finish up with some square minus a term. If we had a plus x squared in there, and just for the sake of it we can do it now, we'll go over to this side and say what it would we expect it to look like. There's a plus x squared here. We are expecting something like this. Because we have a standard answer for that. Now we want to find how we make a square out of this. So let's bring the numbers down here. This is going to be twice the number we need in the factor. So we have 13 plus, and now we will have 4 this will give us x plus 2 in here. But you'll notice we have 4 too many now. 4 and 13 will give us 17, whereas we started with 13. So I will have to take away 4. That's outside the bracket. So I now have 9 plus x plus 2. So this equation up here can now be replaced by we can get into a good habit at this stage. You'll find it gets used a lot later on, and especially in the special question. We could have given a name to this here. We could call it I, being the first letter for integral. And we could say that implies I is now equal to the integral of du all over the square root of 3 squared plus u squared. It saves us having to write all of this thing out again down here. We now have a standard integral, and we can state then that is equal to the log plus a constant, and we can substitute back again now. That's the basic game. We're trying to find standard integrals. We have easy enough methods such as forming squares to help us turn something that looks like a standard integral into a one, and then we simply use a recipe which you will find in the log tables. But there's clearly more to it, and secondly there's clearly need to become efficient in doing this kind of work. And before we move on to all that stuff, I just want to introduce you to definite integrals. Those last ones are called indefinite. Now, for example, if you were really clear about something and you answered the question, you would be definite that you were right. We haven't been definite about our answers in integration up to this, That's why we write in plus a constant, the plus c. So we're indefinite. All of those ones we looked at are indefinite integrals. If we want to be definite, if we want to be certain, we need some other piece of information. And in integration, it's normally supplied. And we'll say we want to be definite. It's applied by way of limits. And we'll explain later on what these things mean. If we get the answer to this, whatever it may be, let's say, for example, we'll pick a very easy one, and we'll parallel it over here with the indefinite, where we had the integral of f of x dx. And we'll pick a very simple example. And over here we look at 3 times x squared dx. What we would have done up to this is we'd say it's 3 by 1 over 3 x cubed plus c, plus the constant because we're not definite. So it was x cubed plus a constant. Over here things are a bit different because we have this extra information of our limits. So we know already what we get when we integrate it. We will have it's x cubed, and this time we don't write in a plus c or anything, but we'd still show our limits. So x cubed, and the limits are 1 to 2. What we do is we start with the top one. Say that's equal to putting in the value for x of 2 cubed, and we will take away the answer from the lower one. Now that's a very definite answer. It's 8. It's a bit like the answer to the life, the universe and all is 42. So we have an 8 here, so we're quite happy with ourselves. Over here we cannot be certain. If you remember the example of the straight line, we get the basic straight line which crosses the y-axis when y is 0. Similarly, for any other polynomial, you may draw it and it may cross the y-axis at 12 for argument's sake. If you differentiated that basic function, you will get the slopes of it. If you now go and integrate that slope equation, you will get the original one, but you won't know what the free number was. You won't know where it crossed the y-axis. This time the exact same squiggly shaped function, you can draw it, but it'll come through 0, 0. Let's continue playing around and investigating integration by substitution. We're looking at this integral of 2x cos x squared dx. What you'll notice now is that we actually have two functions. We have this guy and we got this guy. There's a basic rule that you need to understand. And it's pretty universal that when you have a product like this, you look to the harder function and you will take part of it as being the substitution, the u part. In differentiation, I did mention to you guys that we use, for a chain rule, you can imagine things like an onion. You have to keep applying the chain rule right into the heart of it, from the outside in, until you get to the inside of it. The concept holds a little bit here. What you have to notice is which is the harder and which is the easier. Clearly this function is just a simple x. This one is the cos of x squared. And how we just use this visualization over here is In the more complicated one, which is obviously the cos x squared, you just go in one layer of the onion, and this thing will be your substitution. So cos is the last thing that happens. You start off with an x, you square it, then you cos that. So we step in the outside layer, which is the cos, and we find x squared. So we can say let u equal x squared. This also implies that du dx is equal to 2x. So du equals 2x dx. And the nice thing is we've now found that this bit and that is equal to the du, so we can substitute. That implies that the integral I, because see up here we've named it, it makes life easy for us down here, that's now going to be the integral of cos u du, which is it's plus c because we do not have limits. See, we don't know what this is and we don't know what that is. And we substitute back our u as x squared. It's amazing how easy we can make a function by putting in a substitution. This was definitely a lot harder than that. We can look at a lot more of them, but this one will give you a throwback to comments that I made earlier. What about that one? Do you remember we said that when you're doing integration, don't just look at the table of standard integrals, also look at the table of results for differentiation. What we have here are two things. We have log x and we have 1 over x. Okay? Integration basically is the return journey from differentiation. So what we want now is a situation where we get a link in differentiation terms between that and this. And we know that if I differentiated this, if that was f of x, then this is the f dashed at x. If I differentiate log x, I'll get 1 over x. That would imply that we will use log x as the u. Watch how this works. Just because we've called this u, we now need to differentiate it because we want to find a substitution for this guy, plus other bits. Now, see immediately, as soon as you've named the u, you're going to be differentiating it. And we know that's 1 over x, which implies that du is 1 over x by dx. And this thing is all of that. So it's equal to the integral of u du. And u is u to the power of 1, so when we integrate it we'll get half u squared plus the constant, because we don't know the limits. Okay? And we know what u was, so we'll say it's equal to a half So there's a lesson to be learned here. When you have two functions like this and you're looking to see which one will I, or where or how will I use a substitution, keep your eye on what happens. Once you've declared a substitution, you know, like this guy, you know you're going to be differentiating it. So when you're faced with these two, log x and 1 over x, check, assuming you needed to, check what happens when you differentiate each of them. When I differentiate log x, the differential of log x, I find the answer is 1 over x. That means I have found a link between this top guy and the underneath one here. So the log x is clearly the one that we pick. Look at again to quite a simple one, the integral of 3x squared minus 1 all to the 4 multiplied by x dx. And this time we will use limits 0 to 1. So we do have extra information, which means we won't be doing the plus c when we get an answer. If you remember that onion which we showed a minute ago, we're saying there's two functions here. There's this guy and there's this guy. It's very clear this guy's the harder one. It's the more complicated one. There's more layers to that onion. And what we've agreed is that we step one step in. Now look at the complicated one. If you've got some value for x, you'll get you'll square it, you'll get 3 times it, you'll take 1 away from it, but the last thing you're going to do here is bring the whatever you've worked out, you bring it to the power of 4. So this is one step inside the onion. So that's what we're going to use. Now again, let's call this I equal to, let u equal to 3x squared minus 1. That implies du dx is equal to 6x. Now you will notice up in our integral up here that we don't have 6x, we have just a single x dx. So what we can say, that implies 1 over 6 of a du is equal to x dx. And now we found a means of substituting or replacing that. It's going to be 1/6 of this. I, the integral, is equal to the integral, and we'll look at the limits now in a second, of u to the 4 by du, and we have 1/6 of it. So 1/6 du replaces that, and we have 4. We have u to the power of 4 because we've chosen all of this as our u. Now, we had limits, see, 0 and 1, and we have to change them for our u. So what you do is you just set up a little table for yourself, x and u, and we know u is equal to 3x squared minus 1. When x, and check the lower limit, when x is 0, what will u be? And when x is 1, which is the upper limit. When x is 0, u is minus 1. When x is 1, you get 1 squared, which is 1, and 3 minus 1 is 2. So now we're saying the limits that I did have, which belong to x, will do the exact same thing as these limits when I'm using u. So I can now put in those values. And that makes life easy for us. This function in here we're going to use with the upper limit now, and we're going to get 2 to the power of 5. Sorry a second, it's this function, because I've already brought the 5 out here. So it's 2 to the 5. And we're going to use this one with the lower limit. So we're going to get minus outside of minus 1 to the 5. The answer from all of that is going to be 11/10. So it's substituting the top limit, the upper limit, and take away the answer you get when you substitute in the lower limit. So we're having fun at the moment, being able to make substitutions. We now just need to look at games that gets played. You need to look at the function you have and decide if it's a particular type or another particular type, because then it saves you a lot of time and you become very efficient at this stuff. It's pretty clear that if you have a very simple integral like this, that'll give us a linear substitution. You're saying, won't that be like the integral of a u du? So we could say that makes 2x minus 1 is the u. So that's straightforward. And you know enough about the integration at this stage to be able to proceed. Having put u as 2x minus 1, you differentiate it, so you'll get du dx is 2, so therefore u is equal to 2 dx. So half of du is dx, and you have your substitution then immediately. We've already looked at the completing squares. For example, we know that that looks a lot like the integral of dx all over the square root of an a squared minus x squared. So we want to be able to replace this with a square, and to do that we'll have to sacrifice some of the 12 or add something to the 12. So we just do another example just to keep you clear on it. Notice how this is a minus x squared, so that's why it'll be a minus. We'll put everything we have here into a minus bracket first. And having done that, you'll say, now I'm going to make a square in here, and you will say x plus 2. If I square it, I will get an x squared, I will get a 4x, but I'll also have a plus 4 in here, okay, once I square that. So we're now saying, I have an extra 4 in here, which is inside my minus bracket here, and we'll write it out. That's equal to 12 minus, and we'll multiply out our square now, x squared plus 4x plus 4. If I pull that 4 outside the minus, it means I'm taking it away from the 12, and I want to keep the same free number as I started with. So outside my bracket I must add 4. So I have 16 minus x plus 2 squared. So we'll say it's equal to the integral of dx all over the square root of 4 squared minus and we know how to play with that because it's a standard integral, and we will just get the recipe answer from the log tables for that. remember from differentiation that if we differentiated log x, you get 1 over x. That means we have to be careful on the way back. For example, it has to be a log. Simply because differentiating log gives you a 1 over x. Therefore, if we're integrating a 1 all over a polynomial like this one, which is x to the power of 1 plus a, that's a linear polynomial. In other words, the equation of a straight line, but it has a power of 1. We know that we have to get an answer which is a log, because integration very much is a return journey from a differential. What other kind of ones do we have? If we're dealing with polynomials, that means we're only dealing with things like straight lines, quadratic equations, which are parabolas, cubics, quartics, or any of the other ones that are bigger than that. If we're just dealing with those, and if we're dealing with a rational expression, that's something divided by something else, there's a small number of rules and they're all quite sensible, and once you see the expressions written down, you will, once you know the rules, you'll know immediately how to proceed. So what we're now looking at are these guys. Some polynomial divided by another polynomial. If the power here is the same, if the biggest power of x is the same there as in the function below the line, if it's the same or if it's bigger than the one below the line, we will do a division. So what we're saying, and we'll show you by example, 0 to 2, that power, the biggest x power on the top, is bigger than the biggest x power underneath. So we're going to do a division. It's always worthwhile to fill out terms that may have a 0 coefficient. Makes life easy. And we have a remainder of 5. So we're saying that this thing is the same as the integral from 0 to 2 of x plus 2 plus 5 all over (17) divided by 5 is the same as 3 plus 2 over 5. That's all we're doing here. That is just equal to this. But the nice thing is, it's very easy to integrate that now. It's also easy to integrate this one. It's just like the last example we used. We've already looked at the cases where the polynomial above the line is just 1. In other words, p of x equals 1. And all you do underneath the line, if it's a quadratic, you form squares because you want to find it into one of the basic integral types. Now we want to form a square, and the square that comes out of this is, I know that the minus 6 is going to be twice the number that I want to deal with here. So we're saying x minus 3 is what I'm looking for, and minus 3 squared will give me a plus 9. I had in total 13, I've already used up 9 of them, so I'm left with 4. And that's a standard integral. So the answer is equal to remember your constant. You have no choice because we didn't have limits. You have to put in your constant. You do not have the right answer without that constant. One other little thing you should have noticed, in the cases where, so far, where we've used a substitution, which we generally call u, we transform whatever integral we have. And if we have limits, an a and a b, an upper and lower limit, we find how those limits change with the substitution, what they mean in terms of the u. And when we integrate then, we don't have to turn back to our x equation. We can integrate, put in our limits, and get an answer. If we were to do this by integration, by using a substitution, and call that u squared plus 2, in other words, u equals x minus 3, so du equals dx, so we'd say du. We would immediately be finding an answer to this particular guy, but haven't got the answer. We have to turn back into x's because we weren't asked for u's. So we've looked at 1 over, let's say, an ax plus b, and we've looked at 1 over ax squared plus bx plus c. Now, and we had looked at, for example, ax squared plus bx plus c all over. Those type ones, we know how to deal with those. This one is going to give us a log of some sort. In this one, we're going to find squares. In this one, we're going to divide this by this guy, and you'll get so many whole times and a remainder. And that remainder function is going to be much simpler than this overall function we've here. Now let's look at another type. What do we do there? Well, we know from differentiation, if we were to differentiate this, you will get so much x's to the 1s and possibly plus some sort of a constant. And doesn't that look like this one here? So here, what we'll do is we'll let the whole lower line equal to the u, and we'll proceed on that basis. That's for these kind of ones here, where we've the integral of a linear polynomial divided by a quadratic polynomial. Once I've differentiated this, I'll have du dx equals 2x minus 4, and then I multiply across by the dx. And now what I have is a function here which has a linear polynomial multiplied by the dx. And we go and examine the top part of our equation and we look to see what it's like. And in this case, it's twice it. So we can say a half of du equals the x minus 2 dx. That implies the integral is now, and we look at the limits in a second, it's going to be a half outside of x u. We had 2 and 3. And the u, when x is 2, you shove it into this, and we will find 1. And when x is 3, we'll find 2. So our limits now are 1 to 2. I'll just remove this little bit of stuff over here to make room for myself. So that implies it's equal to a half outside of log of u from 1 to 2, and when I put in the limits I'll get it's a half log 2, because the log of 1 is 0. See? Easy so far. You're about halfway through the chapter now, believe it or not. And we have basically looked at the types of integrals that you'll get that are polynomial based, that are basically just quadratics, cubics and linears. The trigonometric ones have a set of rules of their own, and the little ones that you should remember. For example, in the log tables it will give you the integral of cos x and it'll give you the integral of sin x, but there's no harm in remembering these two. Don't forget the plus c if we don't have limits. For all values of k which are real numbers but k not equal to 0, obviously it would be degenerate solution. You'd be looking just at sine 0 and cos at 0. It wouldn't be a function. So they're all pretty straightforward, those type of ones. Now we want to look at these kind now, where we have cos of an ax by cos of a bx, or cos of an ax by sine of a bx, or sine ax by sine bx, or the first thing you'll probably say to yourself is, technically we have the same one written twice here. It's a cos by a sine by a cos. However, that's not quite true, because there's a little trick you have to remember. When you're given these, and we'll show it by an example, you want to find I, which is the integral of cos 2x by cos 4x dx. The little trick to do to make your life easier is find the one with the biggest value in here and move all of this to the front. It's just to get rid of working out sines or coses of negative angles. It'll save you a step. So we can say that is equal to the integral of cos 4x by cos 2x dx. What do we do with them? All of these are, as you can see, products. And we want to replace products with a sum. Because if we get two functions now, and you split them and they're split because of a sum, it's very easy to integrate them. So let's look at this particular one as the example we're going to pick. This integral here, the cos of 4x by cos of 2x, it's equal to half the integral of cos of 6x plus cos of 2x dx. And you know the four equations that you will have in the logbooks in relation to this. It's the cos of a plus b and sine of a plus b's and minus b equations. Four standard equations. It is very clear that this is now much easier to deal with than having dealt with a product. We already can say to ourselves, I have a 2 outside of. I know what the cos of 6x is, because it's like this thing. And this is a 2x one, so we're saying plus a half amazingly easy. And that really is what you should find as you go through integration. So when you start, you imagine it's actually quite hard. But later on, once you start to practice and you learn basic little rules like this, and you learn to be able to look at something and say, well, that's definitely a product of trigonometric functions. You'd say, I want to replace a product by a sum, which is what we've done here, that plus this in this case. The only thing we have to watch for is to swap the bigger one into the front position. If we hadn't done that, we would have finished up, for example, with a negative value in here. When I get the cos of a minus b, it'll be 2x minus 4x will give me minus 2x. So it'll be cos of minus 2x, and then you have to go and deduce how does cos of minus 2x relate to cos of x. Save yourself the hassle. Do the swap first. Here's another type. Cos cubed x. And obviously the same lesson is going to be learned about sine cubed x. We know that when we differentiate cos we'll get sine, and vice versa. Forget about the whether there's a minus or not at the moment. We know that they're linked. That means that we can split this thing up, and we do know from Pythagoras and from the unit circle, where this is cos of a sine of a. Remember, for our basic unit circle, and you will always see the unit circle on the tables related to trigonometry. We know from this that cos squared, which implies cos squared a equals 1 minus sine squared. So I can replace that by cos x by 1 minus sine squared x. And in this case, we will let u equal to sine x. Sine cubed x equals sine x by 1 minus cos squared x and we can pick up either of those and solve it, but we'll just look at this one. That implies du is equal to minus sine x dx. So now we can say the I, which is the integral of sine cubed x dx, is equal to the integral outside of 1 minus u squared du, and this minus I got from there, so it's equal to 1 over 3 cos cubed x minus cos x plus c. Remember your c. So cos cubeds, sine cubeds appeal to the relationship, the differentiation relationship between sines and coses. There's another set that are called circular integrals. And the reason for it is, well, first off, they're this type. The reason for it is because they relate to circles. We already just looked at the unit circle, but in this case we'll pick a circle with a radius a. And we know you will have a cos of the angle and a sine of that angle here. We also know x squared plus y squared equals a squared. That implies that y equals the square root of a squared minus x squared. So technically this is the integral of y dx. This is just circle work. In these cases you let x equals a sine of theta. Example, the integral of 0 to 3 the square root of 9 minus x squared dx. That's the integral. We'll split it up to make life a little easier for you. The last thing we just need to do with it is, let's look at 9 minus x squared. That's equal to the square root of 3 squared minus 3 squared sine squared theta, which is equal to 3 by the square root of 1 minus sine squared theta. So the equation now becomes a very easy one. We will obviously be changing the limits, and it's the same as the u and x ones. You set up a little table, but this one now just becomes, that implies the integral becomes equal to 9 times 0 to pi over 2 of cos squared theta d theta. Using substitutions makes what are very complicated, or can be very complicated, integrals into things that are very simple. And the process is a straightforward one. There's a small number of rules, and we're going through them systematically. A small number of rules for the leave insert. You make your substitution. You differentiate the u. If there are limits, you set up a little table with x versus u. You use the first limit, you find the change of limit. You use the second limit, find the change of limit, and proceed that way. It is very easy. There is only 2 more sections in this integration chapter before you start to look at integrating areas and finding volumes. And those 2 have to start, we're kind of stepping back a bit again. We're going to look at the integral of a product, but this time the product isn't going to be something as handy as just 2 polynomials, and we're going to look at quotients, in other words rational expressions, some function divided by another, and again these won't be as easy as just polynomials. But you will find the same little rule applies. We find the more complicated one, we go one step in, one layer of the onion in, and we find our substitution. So anyway, let's look at products. That guy, for example. Very similar to what we've looked at before, but you'll find that the same game gets played now. Just so as to keep your mind on the things. Here's our onion again. You find the more complicated one. Clearly, this is the most complicated one here. And you step one layer in, and that becomes your substitution. So it's e cos x. The inside thing is the x. You get the cos of it, and lastly, you bring all that as a power of e. So we expect look down here. Yes, there's a function. Here's another one. The one with the most layers of an onion is this one. You start with an x, you cube it, you take 3 from it, and all of that then is brought to the power of 4. So we expect that is going to be our u. That's an easy one. This is the complicated one. You step inside the last thing that got done, which is the square root, and you find this. They're straightforward. Now then, there's one small group of these that you need to look at, and it's the integral. It can be explained by example. Tan squared x sec squared x. They're both as complicated as each other. So what do? How do you know which side you should let equal to the u and which side will go to forming the du? You appeal to the rules for differentiation. Now we know when we differentiate, tan x, when you differentiate it, you get sec squared. So it makes it easy for us to figure it out. If that's the case, we've a path between this one and that one. So let u equal tan x. That implies du is equal to sec squared x dx. The integral is this. And we saw before, for something like this one, that we do know that there's an equal relationship in differential terms between sine and cos. And what we're going to look for is the one that's in the more complicated expression, which will be this one. So here we'd say let u equal to sine of x. And when we do that, we will find I is equal to the integral of 1 plus u cubed du. All very easily worked out. Last section. Bet you that's a big relief to you guys. We've covered each of the rules so far, and this last set will cover all that you require for the integration for the leaving cert. And when we move on past this little bit into working out areas and volumes, which we'll cover the next day, you will find that the actual integration that you're supposed to be working on is way easier than the stuff we're covering now. This is teaching you the methodology, giving you the tools to do the work. And then when they actually send you out to work out areas and volumes, you'll find that the equations get easier because they're looking to see can you apply them rather than do I know all the rules. Very often in the leaving cert, part A gives quite easy integrals and they don't have limits. And it's critically important to remember the constant bit, plus c. The part B often has very complicated integrals to be calculated, and generally they are testing your ability to recognize what's there, to see that it's similar to something else, or to know what rule needs to be applied to it, and mostly those ones do have limits. And part C very often is a problem, and for most of the last 10 years the problems have been to work out areas or to work out volumes. Quotients. We've already worked out a lot of these guys. Now we're just going to look at ones that will bring in exponentials and logs and perhaps a mix of trigonometry with other items. What's the trick? In these ones, we're going to use all or part of the quotient, okay, as the u. So it could be all or part of this, all or part of this. And the trick is, be guided by the top line. Again, guided by it means what we're using in the underneath should allow us finish up with that when we differentiate it. So look at this one. And we would say two of these guys, so if I drop the 2, so now we know our substitution. If we look at the second one here, you'll notice that in the complicated structure down here, we're going in one layer of the onion again. We're going down in the underneath, and we're also going in one layer. And the reason we're going in one layer this time is we know when we differentiate sign, we will finish up with a cos. And we just back substitute into each of these things, find an easy integral, and solve it. We'll do one example before we finish. It's one layer in here, and we have limits this time. So we've gone one layer in, and we'll say du equals dx. How does that help us? Now the reason I've waited here just for the little bit is all along this is basically the game we've been playing. But here in this case we need to play a different game. What you will find now is no matter how you play around with this, you don't get what's up top. You don't get x dx. It's important to recognize there's one last little rule that you're expected to know. And that last little rule is sometimes the top is got by also playing around with the u. We can also say that implies u minus 1 is x. True? So now I can say that implies from this line here, if du is equal to dx, I can say u minus 1 du is equal to, and u minus 1 we know is x dx. That implies the integral. We'll go and we'll look at the limits in a sec. U minus 1 dx all over there's a small remaining part to this chapter which is just dealing with areas and with volumes. I'll deal with it in a short second talk on integration, and that will also include the first part of the special question, which is only got to do with integration. Now then, I know there's a fair few rules in this chapter, but it isn't hard, as you can see. It's just not familiar, and the only way to turn that chapter into something you can do without much effort is to practice, because practice turns the unfamiliar into familiar. So this unusual little thing that we're playing with is just that. It's just unusual. If you practice, you will turn something you understand into something you know. When you finish with that process, and we only have 2 more of these talks to give, we'll be ready to go through past questions. And at that stage, once you have done your practice, you will start to see the little shortcuts that you can apply to simplify questions in the Leaving Cert, or you will see the standard little methodologies that are used for certain types of questions. And life should start to get much easier for you at that stage. Okay, see you the next day.